Section 7, that's dealing with exponential growth and decay. And growth and decay a lot of times will deal with like bacteria or like different chemicals kind of decaying. But what it all comes down to is growth and decay is how things get bigger and smaller. And we've already dealt with like linear growth and decay. Linear growth would be like a line going like that. So as x gets bigger, so does y. And decay would be like that. And growth and decay are just different words for how they get bigger or smaller. Now, we're not dealing with linear. We're now going on to exponential, which is just a form that it takes. And the graph is more of a curve. And so this is the way that exponential growth works. Okay, so this is the formula. I would get this entire section right here in. Exponential growth can be modeled with y equals a times b to the x. A has to be greater than 0 and b has to be greater than 1. The way that you find b is you take 1 plus the percent rate of change expressed as a decimal. And we'll explain that in detail in a little bit. This is also very important. So a is your initial amount. B is your base, your growth factor, the base for the exponent. And then x is usually like the amount of time, but it's the exponent. Okay. Now, the reason this is called the initial amount is because if we plugged in 0 when x is 0, meaning right here, b to the 0 power is 1, and 1 times a is a. So that's what the value would be at 0, the beginning, the initial amount. So that's where that comes from. All right, so here's our first example. Since 2005, the amount of money spent at restaurants in the United States has increased 7% each year. In 2005, there was about $360 billion spent at restaurants. If that trend continues, how much will be spent by 2015? So we need two things. We need an A and a B because we need to come up with an equation. A is the initial. So the initial, we're starting in 2005. That's the starting point, so that's like our 0 value. So that's 360. B is the growth, which remember is found by taking 1 plus the growth as a decimal. So as a decimal, 7% as a decimal is 0.07. So our growth factor is 1.07, and therefore our equation is 360 times 1.07 to the x power. Well, if we want to figure this out, in 2015, x would be 10, because 2015 is 10 years after 2005. And you would plug that in your calculator, and what you get is about $708 billion was spent at restaurants in 2015 if it continued to increase at 7%. It's a lot of money. We're going to skip this, and we're going to give you a chance to do this one on your own. So go ahead and pause the video. Try this one on your own. Okay. So again, we need an A and a B. A is our initial. In 1985, that's the beginning. There were 285 cell phone subscribers in small towns. 285. It increased at 75%, so that's 0.75. So our growth factor is 1.75, which means that our equation is 285 times 1.75 to the x. They want us to figure out in 1994 how many were there. So that's 9 years later. So we got 284 times 1.75 raised to the 9th power. And if you plug that in your calculator, you're going to get about 43,872 cell phone users or people. Quite an increase. So that growth, that kind of deals with, it could be a number of different things. A lot of times it's used, like I said, bacteria and then how viruses spread, but It's also, things like that, how many people get cell phones and are on the internet, things like that. Another thing we're going to look at is how money kind of fluctuates, and how your money in like a bank account. So some of you may have a bank account, some of you may not, but what we're talking about is a balance is the amount of money you have in your account. Okay. The principal is how much money you started that account with. The annual interest rate is how much money the bank gives you for holding on to your money. The number of times a year interest is compounded. So it's like how many times a year will they look at your money and say, here's some more interest, and here's some more, and here's some more, and then T is the time in years. Okay? So make sure that you get all these variables down. And here's an example. Suppose that when your friend was born, your friend's parents deposited $2,000 in the account. Right there. Let's start right there. So we have A, we have P, we have R, N, and T. Okay? P is the principal. P is the initial amount. So right there, that's $2,000. Okay? It pays 4.5% interest. So there's our annual interest rate. Now we have to write that as a decimal, so that's 0.045. It's compounded quarterly, so that's how many times a year. Quarterly is 4 times a year. So that's N. And what will the account balance be after 18 years? That's our T. And so A is going to equal all of this together from that equation. So 2,000 times 1 plus R, which is 0.045, divided by N, which is 4, raised to the N, which is 4, times T, which is 18. And if we plug all of that in, you're going to get 2,000 times what that comes out to be. Roughly, we'll say 1.01125 to the 72nd power. And when you do that, you get a balance of 4,475.53 after 18 years. So it pays to start early. And then the last thing we're going to look at is decay. And the only thing that changes when it's decay is that you take 1 minus that percent. Okay? So get this in your notebook. Same formula, except this is the decay factor. So it's 1 minus the percent of change. Okay? So if we have a kilopascal is a unit of measure for atmospheric pressure. Okay? Pressure at sea level is 101. And for every 1,000 meters, get this out of the way, increase in altitude, the pressure decreases about 11.5%. We're wondering what's the approximate pressure at an altitude of 3,000. So we still have a few things to do. We still have an A and a B. What's our initial? We're dealing with 101. Next thing is our B. Now this time we go with 1 minus. So what was our pressure decrease? 11.5%. So as a decimal, that's 0.115. So that gives us 0.885. So that's our decay. Okay? That's our decay factor. All right, so our formula is y equals 101 times 0.885 to the x. Now we have to figure out what is x. So every 1,000 meters, and we're looking for 3,000. So basically, how many 1,000 meter jumps is 3,000? And that's 3. So if we plug in 3 for this, we should get a value of approximately 70. And so that would be 70 kilopascals of pressure. Okay, and that is growth and decay.